Okay, next in our review of topics for pre-calculus, we're going to talk about properties of exponents. Why are we reviewing all this stuff? Why don't we just get into pre-calculus? The answer to that is there is so much math. As you know by how much math you've done to get to this point, there's a lot of topics. And no, unless you are doing this stuff all the time, there's so much that people don't remember. And so just having ideas and topics that we're going to use a lot and just review them at the beginning helps us to focus what we're doing and to build from there, to really not on as an exclusion of everything else, but just to refresh ourselves on some commonly used items. So to begin with, before we get into these properties, because we're looking at properties which really are just the patterns that we see in exponents. And math is mostly about patterns. And we want to use those patterns to our benefit, to really understand what's going on and to see things. So to begin with, if I take just actual numbers, because we're going to use a lot of letters to take actual numbers, the larger number here is called the base. The thing we are taking to the exponent, and that's what that's called, is the exponent, the base. Okay, a lot of times when I see people do this, their immediate thought is that's 3 times 2. That's a shorthand way of saying 3 times 2. And that equals 6. But that is not the case. Okay? Even in this level of math, I see this a lot. What it really is that I say that I'm using this 3 2 times in a multiplication problem. So 3 times 3 is 9. So remember this, base and exponent. Alright, and look, I didn't cuss once. Okay, so let's see. Our first rule, our first property is that if you have the base being the same. Now, you'll see on here that I have written down, a lot of these have to do with the bases being the same. And then we have some rules where you have 2 different numbers. Of course, all these rules, even when they're 2 different numbers, actually still work, even if those numbers are the same. But you really wouldn't have them written out separate like that if they were the same, because you would just simplify it to one number. That's why we have it like this, with 2 different ones. Okay, so if those bases are the same, and you are multiplying things, you add up those exponents. If there are no exponents written, so like if you just have 3, there really is an exponent there. Its exponent is 1. It's one of the many, many, many hidden ones in our math life. Okay? So you add up those exponents. Now, if I were dividing them, I subtract the exponents. Now, if I'm taking a number to an exponent, all to another exponent, what I do is I leave the base the same, and then I just multiply those exponents. And boom, there I have it. Now, if I take 2 different numbers, and I am multiplying them together, and I both of them to an exponent, I can separate them out into taking each individual one to that same exponent. Again, the same kind of pattern happens if I'm dividing. I can separate those out into dividing with that separate exponent there. Now, what the heck does that mean, a negative exponent? People are crazy, right? No, I'm kidding. All that means is we're using this kind of rule or our exponent, or just what does an exponent mean, but we're taking the reciprocal of that. So if I have a whole number to a negative exponent, that means make it the denominator of a fraction with that same exponent. What if you have it to a negative exponent, but it's already in the denominator? Then you just take the reciprocal, flip it over, and it's in the numerator. Or it's in the numerator. It is the numerator. Right? Because we are able to write any number, if it's not a fraction, and we want it to be a fraction, we just put that little puppy over 1. And there we have it. And it's the same thing here. If we had this and we wanted a fraction, right, we turn it. This one's already a fraction, so we flipped it over to a non-fraction. Now, if you have two different numbers going on here, and this is really what happened here, number 7 with 6. Because 1 and whatever number, all you do is flip the fraction around. See how the difference? A is now the denominator over here, B is now the numerator over here. That's what happened here. And then you just change the negative to a positive exponent. It's just that here, in this one, the denominator was 1. And so the denominator, 1, became the numerator, right? And here, the numerator is 1. It became the denominator, but it's one of those hidden ones, so we don't write it. So it really is, 6 really is a special case of 7. It's just that one of the numbers is 1. Okay? Now, when we're doing stuff with this, we go back and forth from each side of the equal sign all the time. A lot of people only remember these things this way. But the beauty of this and the real useful parts of this in mathematics comes from using it both ways. And it's a good way to be able to see numbers and manipulate them into stuff that we can use. As we go through this course, you're going to see that a lot. Okay, so being able to go back and forth and just manipulate numbers around to put them in these forms, to then be able to use these properties, is a beauty of math. Just like if I have some problem with the number 9, right? And I'd be like, well, how the heck can I use exponents with that? The thing is, 9 is just 3 squared. Right? So, if I'm seeing a problem and I don't know how I'm going to simplify it, but I have like something like this, I may look at it this way and see, does this help me at all in my problem? Same thing when I'm using just regular variables. Okay, I might use other properties here. I might say, x to the 4th. I'm doing quadratics. How is this going to help me? I can break this down into something like this and use this rule right here and go back and forth. So being able to manipulate these things like this is a lot of the reason to be doing this and trying these out. Alright, so let's take an example and look at this and see how can we put all these to use like this. Okay, so if I take negative 2x to the 5th all to the 2nd power times y to the negative 3rd times z, all divided by x to the negative 7, y to the negative 2, and z to the 5th. I want to simplify this. This is not an equation, so there's no solving for anything. It's just an expression, and so we simplify it. So that's the first thing we notice. The second thing we notice is that all the operations here are exponents, which are multiplication, and multiplication straight out. So a lot of these rules tend to work, as you notice, when it's multiplication. Okay, so here, the first step that I'm going to do is break this down. So I'm going to use this number 3 here and break this down into negative 2 to the squared, and then x to the 5th to the squared. Here I didn't do anything else. I'm just leaving everything else the same. And this is just, obviously, when we want to do math, there's a lot going on here. My brain breaks. I don't know about yours, but my brain breaks looking at that much stuff. So being able to do it one step at a time, leave everything else the same, is perfect. Now, the way I'm also, before I go on, the way I'm doing this is only one possible way. Because there's so many different multiplication problems going on, there's a lot of different ways. The thing is, the final answer needs to be the same, but we can do this in a multiple of ways. So my way here is just one way to do it, okay? So my next step, so I broke those up. My next step is just to say, what is negative 2 squared? That's negative 2 times negative 2. X to the 5th to the 2 power, that is x to the 5 times 2. So I multiply those exponents. And then here, what the heck did I do here? Messing things up. No, I'm kidding. This is a negative 7. So to get rid of the negative, I bring it up. I flip it up to the reciprocal up here, negative 7. Same with this negative third. I bring it down so it's in the where its reciprocal would be. All right, and this z. Now, why did I bring this? This is a hidden 1. Right? Why did I bring this down? It's because this is bigger. So if I brought this up, I'd have a negative exponent, and I'd have to bring it back down anyway. So here, I just brought it down to begin with, and used my exponent rules here. And said if I'm dividing it, I subtract them. Alright. So next, we're going to just tidy up all that math and solve out all these different things that I've done here. So negative 2 times negative 2 is 4. 5 times 2 is 10. Then these stay the same. This stays the same. And then 5 minus 1 is 4. Next, I see these have the same base, x's. So what do I do with those? I look up at my chart and see I add them. So that's what I'm going to do. I am going to take 4, x, and 10 plus 7. And then I leave, of course, everything else the same because that's the only thing I did here. And then 10 plus 7 is 17. And again, I did the same thing with the y's here that I did with the z's up here. This is smaller than this, so I brought this down and said 3 minus this 2. Okay, so then I did that math up. 3 minus 2 is 1. I don't write the 1 because that's one of those hidden ones I keep talking about. And there we have the final answer because there's no... These are not the same bases, so I can't combine any of them up. I have no more negatives because that's a big rule with all this. We don't want any negative exponents. And so there's nothing else for me to simplify. So this is in the simplest form possible. And so we are done.